Thank you for joining us today. We're excited to present the Stand Up project from iGEM TokyoTech 2023. Throughout this past year, we've given our all to ensure the success of this project, aiming for outstanding results in the iGEM competition. However, as some of you may already know, we faced a few technical challenges. Unfortunately, we were unable to update our wiki with all of our findings before the wiki freeze. A quick look at our wiki would confirm this. But don't worry. Today, we'll cover everything, including those missing pieces. So, let's dive right in. Have you ever wondered about this number? This represents the number of dengue fever cases in a single year. It's estimated that each year, between 100 million to 400 million people contract dengue, with 96 million exhibiting symptoms. What's even more alarming is that the number of dengue cases has increased fivefold over the past 20 years. Furthermore, considering dengue is prevalent in tropical and subtropical regions, it poses a significant challenge to achieving SDG Goal 3, specifically Target 3.3, which aims to end the epidemics of neglected tropical diseases, as well as SDG Goal 10, which focuses on social, economic, and political inclusion. Reducing dengue fever cases, you see, is a shared aspiration for all of humanity. Now, you might be wondering, why do dengue fever cases continue to rise? And what can we do to curtail it? To find these answers, we reached out to stakeholders associated with dengue. Through these interactions, we've identified three key approaches: vaccine distribution, mosquito control, and raising awareness. Further discussions revealed that effective surveillance is pivotal to achieving all three goals. So, what's stopping us from implementing comprehensive surveillance now? The current diagnostic methods are low throughput, high cost, and low sensitivity. Our response: we've decided to enhance these testing methods, aiming for high throughput, low cost, and high sensitivity diagnostics. And that led to the birth of our developed methods, CFNT and 3D PCR. CFNT allows us to determine the presence of neutralizing antibodies against the dengue virus in samples. Similarly, 3D PCR can ascertain the presence of the dengue virus, just like traditional PCR. CFNT is cell fluorescence neutralization test. This test is high throughput and low cost than existing method PRN, plaque reduction neutralization test, and high sensitivity such as PRNT. To do CFN, firstly, serum is procured from the test subject, following which an antigen is prepared for the quantification of anti-dengue virus neutralizing antibodies via titration assays. Traditionally, genuine dengue virus particles serve as the antigenic substance. However, our unique single-round infectious particles, SRIPs, offer a safer alternative, given their inability to undergo replication. For the assay, the serum is serially diluted, combined with SRIPs before introduction into a specialized cell line designed for infection detection. The presence of neutralizing antibodies is manifested through observable changes in fluorescence patterns. The underlying mechanism of the neutralization test operates as follows: in instances where neutralizing antibodies exist within the serum, the SRIPs are incapacitated, thereby precluding subsequent infection. As a result, the infection-detecting cells maintain their characteristic green fluorescence, and this image is a result that we get. Contrarily, in the absence of neutralizing antibodies, the SRIPs successfully infect the detection cells, prompting a shift to red fluorescence. Subsequently, the infected cells are distributed into 96 well plates to facilitate the examination of neutralizing antibodies against all four serotypes of the dengue virus. A composite of the serum dilution series and SRIPs is then administered. This allows for the assessment of the fluorescence ratio, which serves as a proxy for the neutralizing antibody titer. Owing to its utilization of pseudotyped dengue virus and cultured cells, the CFND approximates the sensitivity and specificity of the PRND. Additionally, CFND offers a cost-effective and efficient alternative to PRND, thereby enhancing its suitability for neutralization test. The Dry Lab team developed a model concerning the production of SRIP, a core component of CFND. This model is composed of 4 differential equations and was implemented using SciPy, a numerical computing library in Python. Utilizing the experimental results obtained from the wet lab, we adjusted 6 parameters of the model through a fitting process. With the fitted model, it has become possible to predict the time at which SRIP production reaches its maximum. Being able to forecast this peak production time advances the realization of our project. 3D PCR is nucleic acid detection test to detect dengue virus. This test is high throughput and low cost than existing method RT-qPCR, and high sensitivity than RDTs. Let's see an example how to do 3D PCR. Initially, blood is extracted from the subject and aliquoted into wells, a process that is subsequently replicated for 960 subjects. Subsequently, serum samples are collected with respect to each of the 3 spatial axes, X, Y, and Z. This methodology is consistently applied across all spatial planes to accumulate a total of 30 pooled serum samples. To illustrate, consider a hypothetical scenario where 6 positive specimens are identified among the 30 pooled samples, labels M, X, 4, M, X, 8, M, Y, 3, M, Y, 7, M, Z, 3, and M, Z, 6 are discerned as positive. This means that 8 candidate samples would thereby warrant further examination. Polymerase chain reaction PCR is subsequently employed for retesting, to ascertain the presence of true positive cases. Given that the three-dimensional polymerase chain reaction 3D PCR technique is predicated upon the foundational principles of reverse transcription quantitative PCR RT-qPCR, it inherits the latter's sensitivity and specificity characteristics. Moreover, 3D PCR outperforms rapid diagnostic testing RDT in terms of both sensitivity and specificity. In addition to its superior diagnostic metrics, 3D PCR offers the advantages of being both cost-effective and operationally efficient compared to RT-qPCR and RDT. The Dry Lab team has developed a computational tool using Python that is capable of replicating the procedures of 3D PCR experiments. In addition, assuming the availability of prior infection probabilities, we have devised a model that arranged samples based on these probabilities to reduce the number of samples requiring retesting in 3D PCR. Our model has demonstrated the potential to reduce the number of samples needing retesting by up to 70% in certain cases. Furthermore, by calculating prior infection probabilities based on various distributions, we suggest that there is a possibility that educational interventions can reduce the costs of 3D PCR, supporting its economic sustainability for dengue fever interventions in local settings. Through this model, we have substantiated the sustainability of the activities undertaken in our human practice component when implemented in society. In our journey, we heavily engaged with various stakeholders under the umbrella of human practices. We divided our approach into 4 phases: identifying the problem, feasibility studies, ideating the project, and implementation. This rigorous approach ensured we established a holistic loop between our laboratory's internal and external interactions. Moving on to education, a segment we are particularly passionate about. We've been very deliberate about our educational initiatives. After consultations with educational experts, we crafted our unique evaluation metrics and event formats, all of which are documented on our wiki. Let me delve a bit into some specific events. We conducted workshop-style classes at Kuishikawa Secondary School. We challenged these high school students to brainstorm problems solvable through synthetic biology. Over 2 sessions, we assisted them in refining their ideas. With our feedback and direct communications, students proposed solutions, like one team suggesting a protein to combat HIV by inactivating the enzyme converting HIV RNA to DNA. We did this in 30 groups of over 120 students. Their active learning showed us that the future of synthetic biology has great potential. Similarly, we organized sessions at Chiba Prefectural Funabashi High School, fostering further dialogue. We also launched the iGEM TokyoTech internship, drawing inspiration from 2022 iGEM Rumapram teams. That their interest in synthetic biology spiked is evident from our survey results. Additionally, we lent our support to iGEM, an emerging iGEM team in Japan, primarily consisting of middle and high school students. We shared insights and offered them tips to thrive in iGEM. On another front, to combat dengue fever, we crafted booklets educating people in endemic areas about dengue and its preventive measures. Ensuring broad accessibility, we created versions in Japanese, Thai, English, Malay, and Hindi. Although I'm only showcasing the first page here, you can explore the complete booklet on our website. Our ultimate goal: to reduce dengue cases and contribute to achieving the SDGs. We plan to collate data from our surveillance and present it as open source. Such data will aid health agencies, including WHO, to anticipate outbreaks, allocate medical resources like vaccines, and effectively control mosquito populations. It'll also empower locals in endemic areas to understand dengue's prevalence and take proactive preventive steps. By making this data universally accessible, we aim to raise global awareness about dengue, hopefully transforming it from a neglected tropical disease to a global focal point. We've given our all this year and sincerely hope our project can usher in a world free from the shadows of dengue. Thank you.